should probably leave the library at some point and go home, shower, eat. Just become the like Gollum of the library.
I used to sleep in my office in grad school.
Yeah.
Yeah. I would, because we had to teach classes, but I also was taking classes.
Were you just Febrezing your clothes?
No. I was just, it was funny because I'd go teach a class on Monday, right? And then like I go back Wednesday, I'm still wearing the same stuff. It was pretty bad.
Yeah.
But, you know, I looked at it as dedication, I guess. Yeah. All right, y'all ready to get started? Okay, so I really wanted to give a quiz today, and then I had a pretty good feeling that people would be late because of the weather. So I think what's going to happen is at the end of class, the last 10 or 15 minutes, I'm going to give a quiz. And let's see, Carlos, who's meeting with me today? Is anyone meeting with me? No?
I'll meet with you.
I'm supposed to have Carlos Nino Flores. No? Okay, we'll see if he shows.
Can I get that open spot if you got
Yeah, let's see. Yeah, you know what? No, he's probably going to be there. He's probably going to be there. I just realized he's not in this class. He's in the other one. I thought he was in this one. Okay. So, what were we doing last time? Antiderivatives. Yeah, and we had started doing a little substitution, right? Did anybody start that homework, or yeah? How'd it go?
I got stuck on like x times the square root of 1 plus x squared, I think.
Okay. I'm gonna do some more substitution, and I think, I don't want to get ahead of myself, but I think that they have the projector fixed. I mean, at least the workaround, right? Okay, so we'll be able to look at the notes from here on out until they come in and try and fix it and break it completely. All right, so let's get started. We have an example. Let's see, let's get warmed up. Okay, so last class, did we get somewhat comfortable with this notation? Are you okay with this notation? Right, so this is just basically telling you we want to find the antiderivative of this expression. This dx kind of keeps track of our variable, right? And it does actually come into play here as we start to do the actual substitution. So, what did I tell y'all you were supposed to do when you do substitution? What's the kind of the technique?
Find a number and its derivative.
Find an expression, something in here, something, and then hopefully you also see its derivative in there, all right? So we are looking for something in its derivative. Now I'm gonna scroll up here. I have the actual notes from, oh, you know what? This is the wrong section. Ow, that hurt. Let me bring up this one. Let me see. I'm just going to write on the board. Remember, for U sub, look for something. And also its derivative. Okay, but there's a couple things about this derivative that I don't think I stressed to you last time. We're looking in the expression for something and we're hoping to see its derivative also in there. A couple of things about that derivative. You can be off by a constant, which means it's okay if when you look at and you find that something, when you look at its derivative, if that derivative is off by a constant, it's okay. I'll explain that when we do an example. And then the other thing about that derivative, and so I'm talking about that derivative here, is that it can't be in the denominator or trapped in a function. And again, I will show you what I mean by that as we move through an example. So does somebody see something in its derivative here? The denominator is this something? X squared minus 4x plus 8. What's the derivative of that? 2x minus 4. Boom, there it is, right? So this is the first problem, so we're getting warmed up. So this, I think, is pretty obvious, what the something is and what its derivative is. Now let me rewrite this, because I want to talk about this whole be off by a constant and be trapped thing. If I rewrite this like this, then putting this 2x minus 4 kind of slid out here to the side in parentheses, algebraically, I think it's easier for us to see we have 1 over the something, and then we have exactly its derivative, right? And that derivative is not in the denominator, right? Okay, so it's not in the denominator. The derivative is not trapped inside of something. In other words, if this had been, let's say, root, exactly. Let's say that there had been a root around this, like that. Then we would not have been able to do this substitution because the derivative would have been underneath a root, right? Trapped inside something, right? So we would have to do something else, right? All right. So let's proceed. The next step is to say u is equal to whatever the something was. And then we take the derivative, du. Now, last class, did I start writing the dx on the other side? Or did I always write du dx? Okay, I'll just do it. Du dx. I'm taking derivative with respect to x of this, and we get 2x minus 4, right? Now, this is the part that, this step right here, I'm going to skip this step from here on out, and I'm just going to write the next line, which is 2x minus 4 dx. So I'm going to, every single time I do a substitution, I'm always going to write du dx, right? And I'm always going to multiply both sides by dx. So from here on out, I'll skip that and just go straight to this. Is that all right? Okay. Now, at this point, it's just a matching game, all right? You're just going to match things up. You can see that you have your u right here, right? So that's your u. And then the other part that you have to match is the 2x minus 4 dx, the whole thing. Matches exactly with this, right? So I will replace that with du. And we're pretty much there. We rewrite the problem. This becomes integral 1 over what? U. And then this is just du. And so what is the antiderivative of 1 over u? What's that? Natural log u, right? Now, from here on out, I want to make sure that you put absolute value around your, sorry, I forgot my coffee on you. You didn't have any, did you? You sure? Because this has a little bit something extra in it. All right, or did you put something in that? All right. Absolute value around the u, that's part of the formula. And it's because we can't take logs of negatives, so we want to keep absolute value there to kind of wipe out any negatives. Is that all right? All right, and then last step is just replace u in the problem with what it was, which is x squared minus 4x plus 8 plus c. That's it. And remember, you can always check your answer by just taking the derivative. So that problem right there is probably about as easy as a substitution problem can get because the something was very obvious and the derivative was very obvious. Everything worked out great, right? So let's tweak the problem a little bit, all right? I'd like to tweak the problem. So let's start over, okay? And here's what I'm going to do to tweak this a little bit. I'm going to change this problem to x minus 2 instead. And I'm going to put the entire denominator to the 4th power. All right? So when you're looking now for the something and its derivative, why can we not use the x minus 2 as the something? I mean, why would you not? I mean, the derivative of that's just 1, right? And then we still have all this junk down here, right? So it's like you haven't even handled this. So choosing the U, the something, is kind of like this fine balancing act of picking the right thing, right, that's going to work without picking too much. So let me show you an example of picking too much. See if this makes sense. What if I take the entire denominator like this? To the fourth power is my u. What's wrong with doing that? What's the derivative of this? Chain rule, right? So you're going to have the 4 come out. It's going to be all of this to the third power. So you would need to see that somewhere, right? And the problem is you've already called that u. So this is all you have left to work with. So obviously that whole thing to the third power is not up here, right? So it's like we picked too much. So we try something a little less. How about we just take the fourth power out and do that? So the derivative of that would be 2x minus 4. Same thing as last time, dx. Notice I skipped that middle step now. Now, do we have that? Do we have 2x minus 4 up there? I don't see 2x minus 4 up there. Okay, so this is where you have to see that you have it, but you are off by a constant, aren't you? And that's what I mean over there when I say you're off by a constant. If we rewrite this as x minus 2 dx, we would need this to be x minus 2, right? You can factor 2 out of this, though. And if you factor 2 out, and then divide both sides by 2 here, right? This is an important step. If I divide both sides by 2, it's the same as multiplying by a half. So you see what I've done is I've tried to manipulate this expression to make it look exactly like this. See? This is a terrible marker. Right? So these match. That's better. And then, of course, we're going to replace this piece right here, just that piece, with this. So what's the new integral? Careful. What's the new integral? 1 over u to the fourth. And then all of that's being replaced with what? 1/2 du, right? Half of du. So what can we do with that half? Well, remember that when you have a constant, when we take derivatives, constants come for the ride. So when we do antiderivatives, constants come for the ride, right? So what I like to do is put the 1/2 on the complete outside of the integral with multiplication. And then I'll put the du here. What you cannot do, you can never, ever, ever pull the variable. You can never pull a variable out of an integral. Okay, that's not allowed. Only constants can come out. And now you get to take the antiderivative of that. So what do you think? You want to rewrite it first before we do antiderivative? That's really u to the negative 4. Why am I doing that? So I can use the power rule, right? That is not natural log. It is only natural log if it's 1 over u, right? But anything else, you got to use power rule. So this is going to be 1/2 times, let's see, what do we get here? 1 over negative 3, u to the negative 3. And that step from here to here, you should be very comfortable with at this point, all right? If you're still having a little trouble with that, like how we're getting from here to here, that means you haven't done enough of these. You haven't practiced this enough if you're not comfortable going from here to here. And I think we're ready to finish this up. Let's see, this is going to become negative 1/6. How about I write it like this? And then I'm going to take this u to the negative 3, I'm going to drop it to the bottom, so it'll be u to the third power, but u was x squared minus 4x plus 8 plus c. I don't like the way I wrote that negative 1 here. I'm just going to put the negative up here on the 1. Is that all right? Like that? Negative 1/6, and then this is on the bottom also. How's that? All right? Okay. Let's try something else. Okay, that problem's going to look very different than what we just did, right? So tell me what you're thinking when you see that. So you're remembering that in Cal 1, the derivative of something was secant tangent, right? What was it, though? It was secant, right? So remember that the derivative of secant x is secant x tangent x. All right. That's good that you're thinking that, because that does come into play. But you got that x squared on the bottom. That's going to mess things up. You can't do these individually, right? So you can't just like take the antiderivative of this and take the antiderivative of that and just be like, oh, that's it. Did we talk about how many points I would take off if you did that? If you do antiderivative top and bottom separately? 9. It's like 9 out of 10 off. Okay, because that's fundamentally a big deal that if you don't, think through that enough. All right, well, I'm with you on that. That kind of, it's good that you see that, but what do you think for you here? I mean, see, I'm assuming that, well, I'm not assuming. We know this is substitution because that's what we're talking about, right? Do you see how it might be problematic later when we have five different techniques to try and figure out which one you need to use? So you need to see something in its derivative here, and you're allowed to be off by a constant. I think I just gave it away. Well, you can't take it out. You can't factor it. I don't know if that's what you meant, but. So remember I said that you've got to be willing to step up and take a swing at this, right? You have to try a U. You've got to pick something. If you're not willing to like try something and write something down, you're just going to sit there and stare at it. And that's what you're going to do on a test too. You're going to sit there and stare at it for like 20 minutes and realize you're out of time.
Is it the x 1 over x squared that we since the top?
1 over x squared. Oh, you mean like this. Okay, so maybe we can rewrite it like this so that it, I don't know, maybe in your brain this like just resonates a little bit better. That's the same thing, isn't it? Okay. Now, if you let u be 1 over x squared, can I do that? Can we just go down that road? Can I? Okay, just to see what happens. I'm not sure if that's what you really wanted me to do, but if u is 1 over x squared, that's really x to the negative 2, isn't it? Yes. And then if I take the derivative of that, I get negative 2x to the negative 3, and then that little dx that I bring from here. And I don't see this anywhere, right? I don't see that anywhere. So that's where I would cross it out, and I would start maybe with a different u, right? So I'm running out of options as far as what to use for u.
How did you get that antiderivative? Because you're using the power rule.
Yeah, but that was the derivative, not the antiderivative.
So this part is the.
Yes, this is the substitution goes here, and then the derivative goes here.
Okay.
Yep.
Okay.
All right. Y'all don't seem like y'all want to play. That's the same thing, right? Take the derivative of that. Pi is a constant, right? So negative 1 comes out. Negative pi. x to the what? Negative 2 dx. Now, you're doing antiderivative. Derivative, right? So do you see what that is? Isn't that really negative pi times 1 over x squared dx? Isn't that what that is? Do you see that anywhere?
See the x squared?
That's it right there, right? Oh, wait, we're off by a constant. That's okay, though, right?
It's just a constant.
Yeah, so how would I deal with that? How would I get rid of that negative pi? Just divide both sides by negative pi, right? So do y'all see that? Okay, so now this is going to become, let me write it this way. Negative 1 over pi, that's the same as dividing by negative pi on this side. Du equals 1 over x squared dx. When I'm doing a problem like this, right, and I'm looking for my u somewhere, okay, when I see pi over x, I'm already thinking this is like 1 over x. And 1 over x is x to the negative 1. And the derivative of x to the negative 1 is negative x to the negative 2, which is really negative 1 over x squared. That's all happening in my head like pretty quickly. And then I'm seeing x squared down there. I'm going, crap, that's 1 over x squared right here. So like that's all coming together mentally. And that's why I say you have to be pretty comfortable with the derivative, or else it's going to be very difficult to try and go backwards. Now I'm saying that's what I'm seeing, and I've done this for a long time. What I'm trying to get at is that's what you want to get to a point where you're seeing this stuff, beforehand, right? You're trying to, if that was my u, what would its derivative be, and does it fit in here? Before you start writing stuff down. Okay, I think we're good. That's going to be replaced with negative 1 over pi du, right? And then I'm going to replace each of these with u's, right? Okay, so let's rewrite the problem. I have secant u, tangent u, and then this right here is going to be this, and I'll bring that negative 1 over pi out front, and then it's just the du there. And then like from the very beginning, we know the antiderivative of secant x tangent x, right? It's just secant x, so this is going to be secant u, but we have a negative 1 over pi out front, plus c. And then last step is to replace u with pi over x. There it is. Y'all doing okay? Is this 9 a.m. class too early for y'all? What's up?
When you replace the u at the end,
Uh-huh.
I don't know. I mean, in my brain was, I guess, first, I was thinking that you'd replace the. Is that still okay?
These are equivalent expressions.
That's
So you could put that here if you want.
Okay.
You could put this right there instead.
Okay.
But I put that because that's more like what the problem originally looked like, but it wouldn't be wrong. Put that right here. Yeah. Okay, so I think I kind of had you have to think a little bit more on that one, yeah? Okay, so how about this one? I kind of have to make these problems up because I've done almost every example in the book on video, so I have to kind of make them up as I go here to make them interesting. I don't want to redo what's already in the book. This one ought to be fun. Now this one is tricky. This one is tricky. You know what, for the sake of making life a little easier for us, why don't we take the 5 out of here? Let's do that. we'll go smaller steps here.
Could you distribute?
Okay, I was going to ask you exactly that question. Could you distribute this root x through here? Could you? All right. Let me just write what we would have if we did that. If we distributed the root x here, we would have root x plus x root x, right? And if you wanted to, if you really liked, maybe if you preferred rational exponents, you could write that as x to the half. And this one is x to the 1 times x to the half, which is, you add the exponents, x to the 3 halves. So you get that, right? So all three of these are equivalent statements, aren't they? Now, does distributing through here give you anything that you can do, though? I mean, you can't split this into two fractions, right? Can't do it. If you have multiple terms on the bottom and single term up here, you may not split that. So I'm not quite sure that's really going to get us anywhere. Yes?
Can you rewrite the square root on top as x to the negative 1/2?
Could you rewrite this square root on the top as x to the negative 1/2? Yes. So that would be equivalent also. You could write x to the negative 1/2 over 1 plus x, like that. That's equivalent. Now, does that help at all? Does that get us anywhere? We still can't split it, right? Yes. Yes, with multiplication between them. So this would be equivalent. And you are not allowed to do these separately, right? Cannot integrate a product separately like that. So we've got, what, like 5 different things up here, and all of them look like we can't do much with them. But I'm telling you that this is a substitution problem, and you must step up and do something, right? So,
Like u equal 1 plus x?
okay, you want to try u equals 1 plus x? Okay, because why not, right? Why not? I mean, if anything's going to happen, maybe it'll happen with this. So, you know, the instructions for substitution are to look for something in its derivative, right? But here it doesn't look like I'm seeing anything in its derivative. Do y'all agree?
Wouldn't the derivative of that match the numerator?
Okay, yes, the derivative of that will match the numerator. Let's go with this. Let's just see where this leads us, okay? All right. So you're at home, you're trying to do this problem, you make the substitution. The derivative of derivative of u is just du, and then over here you just get 1, right? But it's 1 dx. If you'd like, we can write it like that. Yes? And we do have 1 dx, don't we? Like that's 1 times dx right there. All right, so I will be able to replace this with u, right? I will be able to replace 1 dx with du, but the only thing I have not addressed is what? That root x out there. Like, what am I going to replace root x with? You can't leave x's and u's together. You're either going to do your integral with all x's or all u's. You can't mix the u's and x's because you're making a substitution, right? So everything has to get switched over. So is there anything that you could do? Solve for x here. Take this equation. That's an equation that you have stated is true, right? U has to be 1 plus x. So if I write u minus 1 equals x, that's true, right? Subtract 1 from both sides. And then how about we take the root on both sides? Would that work? Okay. Now we have something we can replace the root x with. Right? All right, so we should be able to rewrite the whole integral in terms of u now instead of x. Let's try. Integral. 1 over root x, which is root u minus 1, and then times 1 plus x, which is u, and then 1 dx, which is du.
So you could just take the root of that, like just out of nowhere?
Where? This step?
Yes.
if you have an equation that relates, like we came in here like kind of like a little bit of like a God complex, right? We're like, we are going to say that u is 1 plus x, okay? We are stating that from here on out, u is 1 plus x. So if u is 1 plus x, then we're free to say that u minus 1 is still x, right? I mean, that's just algebra. And then if I take the root on both sides, like I'm just maintaining equality the whole time, right? Like I'm just doing algebraic moves, so every statement is still true, right? So if I see root x, I can replace it with this, so long as this is my basis for everything, okay? Now, did it help? Did this get any better?
Can we put the u in the root?
You can put the u in the root, but when it goes in, it has to get squared on its way in. So imagine that you push that in here, and so you'll have a u squared going in. So that'll become u cubed, and that'll become minus u squared. So your integral will now look like this. Square root u cubed minus u squared du. And you can't split that up either, right? You can't break that root apart. So what do? You change your major. No, you come on, you got to be, this is what you engineers and computer scientists have to do. You have to solve problems. You have to be willing to try something.
Can we just distribute the denominator?
I think we need to give up on this one. I think we need to give up on this u. I think we need a different u. It's not leading us to anything good, right? I mean, I would argue that this is worse than what we started with. Because, what are you going to do? What do you say, distribute what? Were you saying up here or back here?
I mean, either way we have right now, so it's more.
Yeah.
And I'm sorry, what are we trying to do here? Take the derivative?
Antiderivative.
Derivative at this point.
Antiderivative.
Okay.
Right? Antiderivative.
Yeah.
Can you let u be x negative 1 half?
So you're looking at this 1 over root x is x to the negative 1/2?
Yes.
Could you do that? Yeah, you could. Absolutely. I don't know. I know what the correct substitution is, or else I wouldn't have made up this problem. So, I don't know. Do you want to try it?
Sure.
Okay, let's try it. Does anyone know what the correct substitution is? Like, feel good that they know? Because if not, I'm just going to keep following y'all down whatever roads y'all take me. Okay, x to the negative 1/2. That's what you want? Okay, x to the negative 1/2. Now, I think just so everyone sees, what he's doing is this. He's rewriting this as 1 plus x, and then taking that x, well, I guess we could just put it up on the top. Yeah, let's just do that. Right? That's just rewriting the original problem. That fair? All right. Take the derivative of this. Derivative, not antiderivative. Negative 1/2, u to the what? Negative 3/2. We're taking the derivative, right? Not antiderivative. And then dx. I would start to feel a little bit concerned if I were you in this position, because I can replace this, right? Like I'm good with that. But look at all this stuff we've got here, right? We've got all this stuff right here that I don't see anywhere in this expression, right? Like I don't see x to the negative 3/2 anywhere in here. And I'm not quite sure algebraically how I could ever make that look like anything like that. Do you see that? So, okay, strike 2. Or are we on strike 3? Was that strike 2? Are you okay with yourself picking something and being wrong and starting over? You have to be in this class willing to accept that you are going to try and fail and then retry. Yes?
I have a question.
Yep.
This thing that we just had.
Which one? The one before?
Yeah.
What about it?
So it's going to be the 1 over the square root of u to the third.
Minus u squared. Uh-huh.
So we were to rewrite it as u to the 3/2 minus u to the 1/2.
You can't, because the root extends over both, and what you would be doing there is splitting it into 2. You cannot do that. But even if you could, even if that algebra was correct, you can't bring those up because it's 1 over the 2 thing, so you still would be stuck. All right. Who's taking the next swing? Okay, what do you got?
So we were thinking about what if you separated it into two integrals? Is that possible? Like
1 over the square root of x times 1 over the 1 plus x.
Like this,
dx
dx, and then times.
integral of 1 over 1 plus x.
Now don't take this the wrong way, okay? But this is minus 9. This is exactly what you can't do, okay? Is everyone clear on this? What you've done here is you've taken a product, right? You rewrote it as a product. Okay, you rewrote it as a product. That's okay. But this cannot become this. It would be great if that's the way calculus was, all right? Cal 1 would have been a lot easier if product rule wasn't product rule, right? If product rule, it was just take derivative of each one and multiply, like. And Cal 1 and 2 would be a lot easier if those weren't the rules. This right here is basically you taking the antiderivative of a product by just doing does that make sense?
Yeah.
Okay. So, no go. Sorry.
So what if from the top one you were to square it?
Oh, good.
Entire function?
Square. Okay, I'm glad you mentioned that. Someone in my other class mentioned that also. So check this out. Let's say that I want to, let's just take an expression like 4. All right? If I square it, is it the same thing? It's not, right? But all your life you've been told you can square things, right? And nothing, it's all okay. Just be careful. When you've ever squared things, it's always been an equation. Okay, so you've always had x is 4. Now, if you square both sides, you get 16 is x squared, right? Now, have you still maintained the relationship that x is 4 here? Yes, you have. But if you just take an arbitrary expression, 4, and then come in here and square it, it's 16 now. It's not 4 anymore, right? So when I look at this integral, I can't just square the top and bottom and it's the same thing. You have now changed what it is, and there's no way back. Like you might think, I square it, integrate it, then square root it. Nope, it doesn't work that way. But that's a common thing also that people are trying to get through this, what can I do algebraically? Look, I'm telling you, there is a u that works. Yes?
Could the u be 1 over 1 plus x?
1 over 1 plus x? Could it be? It can be anything you want it to be, man. Anything you want it to be. There you go. Can I use that? That all right with you? Derivative of this? What's the derivative of that? Negative 1 to the what? Oh, crap. Do you see? I mean, that's here, right? That's this. That's going to be u. But now this is in here. Like the derivative. Do you see that anywhere in here?
Nope.
Nope. Okay, strike 3.
We're not guessing.
We're running out of options.
Pretty sure once you tell it,
I don't think you'll be disappointed. I think you'll be more like, that's why we have to learn. Like that's why someone has to teach us sometimes, or show us. I shouldn't say teach. Show you, because it's not very natural. Maybe yes.
In Cal 1, with the regular derivatives, you had product rule. Is there something that you can do with this? Like, is there some?
We're doing it. We're trying. We're trying to undo the product rule. We're trying to, basically, we're antiderivative here. We're trying to undo. See, we don't know where this derivative came from, right? Like, we are looking at the derivative of a function, and we're trying to take it back. We don't know if it came from a product, if it came from a quotient, if it came from a chain rule. We don't know exactly by looking at it where it came from, all right? So when we're trying to undo it, there's not like a rule to go back.
Yeah.
There's not a product rule for antiderivatives. There's not a quotient rule for antiderivatives. Sorry.
So I think if it was a product rule, it would have two, or some things being added, or it wouldn't be like just multiplied at the end. Usually it's not. You know what I'm saying? Like when you use the product rule, you have the.
You always have like an addition in the middle.
Yeah, then you can combine them or.
See, but that's the thing. If you combine them, then you lose that addition somewhere in there. So it's harder to see it come out.
But I don't think it would be two things being multiplied.
Yeah.
So maybe it's a.
You could have something being multiplied. It could happen.
Just trying to think of something.
All right. You're not allowed. I thought you said you were out. No, I'm kidding with you. What do you got?
Because if you multiply the denominators of that original function,
Yeah.
once the derivative of hyperbolic arc, hyperbolic sine is close to that.
Close.
So that's why I'm guessing that it has something to do with it.
There might be a way we can get it with some weird formula or something, but there is a basic substitution here that will work. Nope. I need someone to give me a u. And every u I've been given has not worked.
U equals 1.
Okay, u equals 1. du is 0. du is 0, right? And 0 is actually not there, so you can't use that one. Strike 4? See how many strikes we get. What do you got?
Can you make the whole bottom?
The whole bottom? What would the derivative of that be? A lot, right? And it's not there. What have we used? We've used 1 plus x. We've used x to the negative. How about root x? How about just root x?
You tried that one?
No, we haven't.
We have not tried that.
Tried to run over.
We tried x to the negative 1/2.
Oh.
All right. Now, let's just try and think ahead here. All right? Well, let's not think ahead. Shit, let's just try it. du, what's the derivative of this? 1 over 2 root x. Oh, man. Okay, so now it still looks like we messed up because this is kind of what you were choosing your u as, right? And so you were thinking maybe this will be 1 over u, right? Is that not kind of the idea here? 1 over u? And then looking for its derivative, but the derivative is this. But look,
You
it's...
can pull a constant.
Yes, we can get rid... I don't care about the 2 because I can multiply both sides by 2, right?
Yeah.
Yeah? I think initially, I'm thinking this is 1 over u, right? Initially. But the derivative's not here because I'm already using that. However, how can I rewrite x? U squared is x, right? Huh. Do y'all see that? That's the original problem, right? Do you see that? Let me see. Let's multiply both sides here by 2. Can we do that? 2 here kills this 2. Do you see now 1 over root x dx, 1 over root x dx matches exactly? Yes? And what can I replace x with? U squared. Arctangent, yes. Look, this new integral becomes 1 over 1 plus x. What's x? U squared. And then what's all this red stuff? 2 du, right? 2 du. There it is. What? You're not liking it? Yeah. No, I can see it on all your faces. You don't have to say anything. I mean, this is the reality. I told you, like, Cal 2 is very different than Cal 1. I mean, this is the reality of the way it is. You know, nothing is just cookie cutter, follow this procedure and you'll be there, right? Everything requires more thinking. Trial and error, but with some thought. Now, let's go back and think a little bit more. Well, see, now that you see it, can you see that this right here, can you see that that's really root x squared there? Can you see that now? This is root x squared right there. So what's the derivative of root x? 1 over 2 root x. 1 over 2 root x. I'm off by a constant. It's hard to see it. But now you know, right? Now you know that, like, okay, I've seen him do that before. So what's the antiderivative of that? 2 arctangent of u plus c. And then replace u with whatever u was. What was u? U was root x, right? There it is. I'm just the messenger, okay? I'm just the messenger. This is it. I'm presenting to you what Calculus 2 is about, all right? Don't get mad at me. Yeah, we'll do another one. You ready?
So basically, you just have to look through all the like parts with variables and find out which one to make it easier.
Well, in the first problem I gave you today, something as derivative was sitting there staring at you, right? Just like, hello, I'm right here, you know, right? The second one I gave you, we were off by a constant. We had to deal with it, right? But the last few I've given you, we've been required to use a substitution that's not as easy as that. But trying enough persistence, we were able to get to it, right? So I would look at this more as like the persistence part than anything else. Try something, it doesn't work, try something else. And the more you do, the more you'll start to see it before you do it. Okay, how about this one? You can do this, all right? You just have to raise the bar for yourself. And you have to believe that you can get, like, your brain can actually figure this out, all right? How about this? I'll go as far as saying that this actually, for people who like challenges and like almost like puzzles, not puzzles like puzzles, you know, like things to solve, like this can actually be very rewarding and very kind of fun almost, all right? But you will suffer for the reward, all right? Hasn't math always been like that for you? Like when you get it, like you feel good about it? You feel like, yeah, I understand this, you know? The rewards get greater, but the effort it requires is more. Yes?
The derivative of tangent x is secant squared x?
Are you asking me or telling me?
I'm sure. Right?
You're sure?
Yeah.
Yes, I agree. So the derivative of tangent x is what? Secant squared x.
And we have 1 over cosine squared.
And 1 over cosine is secant, right?
Yeah.
So 1 over cosine squared is secant squared. So what do you want me to use for you? Tangent x?
But we can probably add that.
You can probably add the 5. All right. So u is 5 plus tangent x. So I was trying to sneak that cosine squared in there to try and make it so it didn't look like a secant squared. But what has been already revealed is that 1 over cosine squared right here, this is really secant squared, right? So if we use u as 5 plus tangent, do you see why picking the 5 up is worth it? Okay, we don't lose anything in the derivative, right?
Because it just goes away anyway.
Yeah, exactly. All right, so I think we can start matching things up. Like this is 5 plus tan x, that's this. And then this right here, this whole thing is this whole thing. Still trying to figure out where the smell in this room is coming from. I tell you, every time I come in here on a Friday, this room does not stink as bad. As bad. It still stinks, but it's not as bad. I'm not saying it's any of you, but, no, you're getting used to it, I think. I think we're all of our senses are getting fried. All right. So look, I think this one is pretty straightforward now. Yeah? Integral 1 over u. Excuse me. 1 over u. Natural log u. But what was u? 5 plus tan x. How are you going to get good at this? Practice. Practice, practice, practice. Don't just watch my videos and be like, oh, okay, he's going to find that substitution for me. Right? You need to find the substitution. One more and then we're going to move on. Because really, I can only show you so much, then you just got to get your hands dirty. So, all right, here we go. This one. Sine to the 5th theta. I'm using theta instead of x. Cosine theta d theta. So the thetas are x's, basically. This one is not any harder or crazy or anything. Just I wanted you to kind of see something like this. Yes?
Could u be cosine?
Yes, u could be cosine. So if u is cosine theta, what is the derivative of that?
Negative sine.
Negative sine theta, right? Then I need to write d theta over here, not dx, right? So what do y'all think about that?
Yeah, move the negative side.
The negative could come over,
Oh, okay.
right? The negative, I could get rid of that. I can multiply both sides by -1. But that isn't that derivative, the sine is to the 5th power, isn't it over there? Doesn't that mean it's kind of trapped? Like that derivative is to the 5th,
That's true.
right? This may as well put a root over that. I mean, it's trapped. So
That's gotta be sine.
So could we use u as sine instead? Do you see the difference between the two? Like here, this right here is to the 5th power. See the theta, the d theta is not to the 5th power. So how would you do that? Okay, so let's try a different u sub. Sine theta, derivative of that is just cosine theta, d theta. And that I have exactly, don't I? I have cosine theta, d theta right there. And then I've got my sine to the 5th power right there. So I showed you this example exactly for the reason that I was hoping that we would look at both of these scenarios. Right? So you can see this one might work, but it looks problematic. This one works and it's straight away pretty clear, right? Okay, so let's rewrite it. Integral u to the 5th, right? du, straight up. No, because I'm replacing that with u's, right? So the antiderivative of that's 1/6 u to the 6th plus c. But what was u? Sine. So sine theta to the 6th plus c. There we go. 1/6 sine theta to the 6th power plus c. By the way, just so you know, there is a way to do it with this. You could use this, but it's a lot more difficult. And we will cover stuff later in this class. It'll come after the next topic where, like, how would you deal with this if this was like sine to the 5th cosine cubed? Like, how do you deal with something like that? That's coming. So this would work, and we'd be able to get through it. But it's much harder to do it this way than it is this way. Okay, questions? All right, I'm ready to move on. Let me motivate the idea here. Look at that integral right there. X times sine x. What we're about to do now is get to our third kind of approach. I guess it's our second approach, but we have the power rule, don't we? The power rule, if we have x to a power, we're in business. If it's by itself. if it's something we recognize from Cal 1, like secant x, tangent x, right? If we recognize it, we're in business. After that, we had u substitution, where we're looking for something in its derivative. And we've already seen that can be a little challenging. But now, I'm going to give you our next method, but let's confirm that we cannot do this with anything we know yet.
Is this the next section?
Yes, but I haven't officially started. I just want us to entertain this integral and eventually for us to surrender to it and say we can't do it. So you are not allowed to split this into two, right? Cannot do that. In multiplication here, you're not allowed to do them individually. Are you convinced as to why you can't do that? And let me just show you. What would happen? What's the antiderivative of this if I just did it by itself? 1/2 x squared. Okay, times what's the antiderivative of this? Negative cosine? So I'll put the negative out here and then let's just put cosine x here. If you did them individually, that would be your antiderivative, right? Okay, so take its derivative.
Oh, it wouldn't be
Antiderivative,
Oh, yeah.
right? So if you took the derivative of this, you'd have product rule, right? So the first thing you would get is negative 2x cosine x. I don't see that over there, right?
And then u substitution wouldn't do anything either.
Well, okay, so you try a u, right? What are you going to use for u? If you do sine x for u, what's the derivative of sine x? Cosine x, and it's not there, right? What if you use x? What if u is x? We've never done this before, have we? U is x. Then what's du? 1 dx, right? Hey, look, I have dx, I have x, right? I can rewrite this. What do I get? U sine u d u. I've rewritten the problem. I've replaced all my x's with u's. Congratulations, you've done nothing, right? So the u equals x is never really a substitution we even entertain. But I think I've exhausted like all the different ones, right? Like, what else am I going to choose for u? The whole thing? Pick the whole thing is u. Then the derivative of that is a product rule, and it's not there. So do we all agree that does not appear substitution is going to work? Right? Okay. So we now get a new method called integration by parts. And on my list of difficult techniques of integration, the hardest, I believe, is partial fraction decomposition. The next hardest is trigonometric substitution. And then third on the list is this one. It's not that hard. It just gets, there's lots of room for error in something like this. And you still have to be somewhat insightful when you do it. You can't just like plug and chug. So let me show you where integration by parts comes from, all right? I'm going to show you because it actually is a formula, but don't get too excited. All right, here we go. So look at this. You know in Cal 1, if you had two things that were, let's say these are two functions, u and v. If I asked you to take the derivative of that, you would apply the product rule, wouldn't you? Okay, so the derivative of that would be something like the derivative of u times v plus the derivative of v times u. Or maybe you learned it where these were flipped, or maybe they're different. It doesn't matter. You're going to do the derivative of one of them times the other one, right? Then plus the derivative of the other one times the other one. So as long as you've got that in there, it doesn't matter what order they're in. Agreed? So the derivative of a product is this. Now, what would happen if I integrate a derivative? So if I take the derivative of something and then integrate it, I go back to where it came from, right? So what I'm going to do now is I'm going to integrate both sides. So I'm going to integrate this side and integrate this side, right? Understand? What should I get on the left-hand side? What if you take u times v, take its derivative, then take its antiderivative? U times v, right?